Welcome to New Planet School. In this video, I'm going to cover how to solve differential equations in MacGrapher. So, what does MacGrapher actually do? What it does is it can solve ordinary differential equations, or ODEs, I will call them in this video. It generates only numerical solutions, not analytic solutions or symbolic solutions. It doesn't know how to do that. And it only does certain types of ordinary differential equations and plots them in a certain way. And so at the end, I'll talk about some of the peculiarities of MacGrapher. And finally, what it does once it has its solutions, it plots the results, and you can easily export them to any document that you want and send them through email, whatever you want, just like MacGrapher is famous for doing. Okay, so let's review what an ordinary differential equation is so that we're all on the same page. An ordinary differential equation is obviously an equation that contains a derivative. But in particular, it contains only a derivative with respect to one variable, a single variable. Now there's another type of differential equation. The other main class is called partial differential equations, and those are quite different. Let's compare them. This is what an ordinary differential equation looks like, and this is one that we're going to look at a lot. It's the harmonic oscillator equation. It's obviously an equation. It obviously has a derivative, in this case a second derivative, and it's with respect to one variable, t here, which maybe is time. And so it's very simple. This wave equation here is an example of a PDE. It's also an equation. It also has derivatives, but they're partial derivatives. That's what the symbol means, because there are derivatives with respect to two variables, x and t. And MacGrapher does not do partial differential equations at all, so we will be focused on this type of equation in this video. Okay, so it's important to review how we specify an ordinary differential equation. Obviously, you need to have the ordinary differential equation itself, but typically that's not enough. And most of the interesting features of ordinary differential equations come due to the initial conditions or the boundary conditions. But sometimes you might find a general solution, like these are exponentials, these are sines or cosines. That's interesting too. But what MacGrapher does is it wants to give a very specific solution for a different set of initial conditions or boundary conditions, depending on the type of problem that you're trying to solve. And what's nice about MacGrapher is it gives you those specific solutions, but you can give a whole range of initial conditions to see what the whole family of solutions actually looks like. It's pretty good. So just to put that in writing, we have our ordinary differential equation. Again, this is the harmonic oscillator equation, and we're going to have two initial conditions. And MacGrapher understands this, and so you need to be prepared to provide the whole set. Okay, all right. All right, so it's important also when you use MacGrapher, it's not just a black box. Solving differential equations is actually a fairly difficult thing to try to do. It's a whole subfield of applied mathematics, and so you need to be a little bit in control of what you're doing. So you're going to specify the ordinary differential equation, you're going to specify the initial condition, and then what does MacGrapher do to get a solution? What it does is it numerically solves the ordinary differential equation you gave it for those initial conditions, and then it generates the plot that you're looking for. How does it do that? Unfortunately, you need to know a little bit about how it does that so you have a little bit of control that you're getting the right answer. So as I say here in item 4, MacGrapher might use the fourth order Runge-Kutta method. And here is how I know that. Once you've entered and then selected the differential equation, you can go into the inspector where you have all your control and see what it's doing. So you can control, obviously, the line, thickness, and color as usual, but more importantly, you can also see which integrator it's using. And you have two choices. One is Runge-Kutta fourth order or Euler. Now there's different types of Euler methods. I don't know which one this is using. Maybe forward Euler, I'm not sure. But there's two different solution methods you can pick. And you can pick the step size. That's really important. As you'll see as I go through this video, picking the step size is very important. And really important is that when you pick the step size, make sure you refresh it. Every time you change something, it resets to the defaults. You have to reset the step size, and then you have to tell it to recompute. And you'll see that in this video. I go through that step over and over and over again. Now, you're probably asking yourself, why do I say it might use the fourth order Runge-Kutta method when I can clearly select between these two? And I'll show you later from my version that I'm using. And my computer is pretty up to date right now. It doesn't matter which one I pick. I get the same solution every time. And I'll show you that later. But no matter what it's doing, you need to be responsible for setting the step size. And you'll see what I mean as I go along. The step size really dictates how accurate your solution is. So keep that in mind. It'll be obvious as we go through. Okay. Now, MatGrapher solves 4 types of ordinary differential equations. Very nice. The first 2 are very simple, first order and second order differential equations. And it also solves coupled differential equations. Now, it calls these 2 in the first category implicit, and it calls these, the coupled ones, explicit. I'm not going to use that language because in the field of numerical differential equations, the word implicit and explicit, they have very specific meanings, and they're different from the meanings that MatGrapher uses. So I'm just going to pretend like those 2 words aren't there. But most importantly, just keep in mind you can do first order, second order, or first order and second order coupled differential equations. Okay. Alrighty. So let's do the simplest example, which is exponential growth. So I have a simple first order differential equation here, dy dt equals 2y. I have to specify an initial condition. And luckily for me, this is also an equation I can solve analytically. And so this is what I think I should be getting. Now, this brings me to an important point, or 2 important points about MatGrapher, is that it uses very specific notation. In this video, I'm going to switch back and forth between different notation, and this isn't to confuse you. It's so that you get used to the idea that when you write your equations down on a piece of paper and you translate them into MatGrapher, you got to think about what you're doing because the notation is going to change and you don't want to confuse yourself. So for example, I'm using what I would call the Leibniz notation for the derivative here, and MatGrapher doesn't do that. It always uses the prime notation. And so that's one simple translation you have to do. Another translation you have to do is I'm thinking about this as some variable y that's varying in time. MatGrapher will always use y versus x always. And so whatever your independent variable is and your dependent variable, you're going to have to write them down as y versus x and just don't get confused. That's just what MatGrapher does. Okay, so now let's actually try using MatGrapher to solve a differential equation. Very simple, open MatGrapher. We want to do a 2D graph. And what we're going to do is go down here to the lower left and go to the templates. And within the templates, it'll say differential equation, and we're going to pick the top line, first order. And we simply type in our initial condition. As you can see, it needs the initial condition and it needs the differential equation itself, and press the return, and there is our solution. It's that easy. So one of the things we can do is always, when you first get started with MatGrapher, pick an equation that you already know the solution to so you can type it in and make sure that you get the same result that you think you should be getting. Here I'm going to add a little bit of a shift just so you can see that in fact those are giving the same answer. Yep. So MatGrapher is working. It's solving a first order differential equation, and we verified that it's giving us the solution that we would like to have. Okay, now the other thing that's really nice is the role of the initial conditions is really important, and we can specify a range of initial conditions in MatGrapher. So I just defined this variable alpha, typing in some possible initial conditions here, go back to the differential equation, change the initial condition to alpha, and we get a whole family of curves. And that's really nice because you can see how the different classes of solutions of the equation is determined by the different initial conditions or boundary conditions or however you're interpreting that. So that's a very nice feature. Okay, so let's do something a little bit more interesting. That was very easy. Let's look at nonlinear differential equations and see what MatGrapher does for that. So again, we're just going to do the first order. We're just keeping things simple right now. And we're going to type in our equation in our initial condition just to get started. Okay, so we're back where we were. Now, what's really nice is it gives us a solution so quickly we can do things like add a bunch of initial conditions as before, and we can change those. Let me type in a few here, 0.2, 0.4, and then I'm going to type in these three because I have three solutions here. Let me get rid of this. Okay. Now, imagine I start changing things. Like, what if I had y squared? What would that look like? Is that what you'd expect? What if I put a minus sign here? Is that what you'd expect? You get solutions so quickly with this, you can start building your intuition. What if I put a minus sign up here? Very different solution. And you can put other nonlinear terms in here. Let me put this back to y and multiply by, say, cosine x. And you, in some cases, you might be able to get an analytic solution and you can compare these. But in some cases, we can make these so complicated that you probably can't. Like, for example, let's put an x squared in here. And you can start to get very complicated looking solutions. Let me move this so you can see it. Let's add some more conditions just to fill this up. We use this triple dot notation starting at 0.2 up to 1.2. And you can see MatGrapher very capably solves nonlinear ODEs for a range of initial conditions, and then you can customize your graph and export it as usual. Okay, so that gets us to second order ODEs. Now let's solve a second order, and let's go back to our example of this harmonic oscillator with these initial conditions. Okay, now this has a solution that you can write down. This is the general solution for the initial value and the initial value of the derivative. If we have these two values, the specific solution is just simply cosine omega t, because this is 0 from here, and this is 1 from here. So that gives us a way to check what we're doing. But as usual, we want to know what a whole family of solutions are doing. So in general, we're going to want to vary these over some range. Okay, so let's try to see how that works. So again, you go into MatGrapher, go under 2D graph, and we're going to go back to the template, and instead of choosing first order differential equation, we're going to choose second order differential equation. That's the second line. There it is. And MatGrapher knows that it needs two initial conditions, so it asks for them. So we can specify the equation itself. I'm just going to, for this example, I'm just going to set the omega naught equal to 1, but you could put some value in there if you want. Specify the initial value and the initial slope or derivative. And sure enough, we get a curve that looks a lot like cosine of t. But remember, we have to put an x here because everything we have is going to be y versus x. And there I just proved to you that it got the right solution. Okay, now, as usual, even though we have two initial conditions, the value and its derivative, we can also vary those independently. So now what we can do is add two equations, one with a range over alpha, which is the initial value, the value here when x is 0. And then we can also vary the initial slope, which is beta. So let's add that one in now. So let's make this a beta. And now we get a lot of different solutions. And that's one of the nice things about MatGrapher, is that it can vary all of those. And at some point, if you put too many values in alpha and beta, it may not like it, but you can do that too. Let me show you how that happens. Omega, I'm going to give it a range. So now we're varying over 3 different frequencies, 3 different initial conditions, and 3 different slopes. And so it can get quite messy, but I think you get the idea. Okay, moving on. Let's go to a real physics example, which is a harmonic oscillator. And this is going to illustrate coupled ODEs. Now keep in mind that this example is the same equation as we just looked at, but now it's going to be in terms of slightly different variables. Okay, so what I'm going to do is I'm going to write it this way. Now notice I'm using the dot notation, where the 2 dots means second derivative with respect to time. Again, I'm not trying to confuse you, but you might actually be writing your equations this way. And instead of y, I'm calling it theta, because now I'm very much thinking about it as this angle. That's important. And for a physics example, omega naught, if you're doing physics, might be the square root of the acceleration of gravity divided by the length of the pendulum. But if you're not doing physics, it doesn't matter. Just think of omega naught as some number. But what we want to do is take this equation, which is the equation we just did with the second order solver, and we're going to solve it now as a first order coupled solver. Now the way we do that is we take this second order differential equation and we write it as 2 first order differential equations. And the usual way to do that is to take the variable you're solving for, theta in this case, and write it as theta dot equals something. In this case I just called it omega. And obviously omega is the rate of change of the angle. So it's kind of like it's not kind of, it's an angular velocity. Think about it that way. And then I take that and take the time derivative of that. That becomes my second equation. And if I take the time derivative of this and make sure that it equals the original equation, the right-hand side needs to be this here. And then I have some set of initial conditions that, of course, I'm going to vary to see what types of solutions I get. And so now I have the same equation, a harmonic oscillator equation, written as 2 first order coupled ordinary differential equations. So let's see MatGrapher do that. So what we do is we go into MatGrapher again. We're going to choose from template differential equations, and we're going to go now to the 3rd line down, which is this first order coupled differential equations. I get this more complicated looking structure. Now I'm just going to define W0 to be 2 because I don't want to vary omega naught. So I'm just going to fix that. You can change that. You can vary over it, and if you want to play around with it. But I want to vary over the initial conditions and leave that fixed. So let me type this in. So there's I'm just picking some initial conditions here, and I get these circles. Now this gives us a great opportunity to see how MatGrapher does the numerics. Notice as I go longer and longer, I start to spiral outward. And if you solve this analytically, what you'll find is I should be getting something like an oval or a circle. Notice also here Euler and fourth order Runge-Kutta don't give me different solutions. I always get the same thing. If I change the time step, however, I do get a more accurate solution. Here I'm going to try Runge-Kutta again. Doesn't change anything. Maybe it works in your version. It doesn't work in mine. Okay, change the time step even smaller. And let's see. Okay, it's starting to look like the oval that I should get. Remember, this equation can be solved analytically, so I kind of know what the solution should look like. We'll do the nonlinear version in a minute. Okay, so let's just vary some of the initial conditions here just to play with it. Notice that it spirals outward now. Every time you set a new initial condition or you go out for a different length of time, it resets the time step. So you have to constantly go in and reset the time step. So what I do is get everything nice and set up. I know it's not that accurate, and at the very end I go in and change the time step to get the real answer. Okay. So let's now do a more realistic example. Let's do the nonlinear version of that. Now that equation was the equation for a harmonic oscillator, but a real pendulum, or something closer to a real pendulum, let me be careful, actually has a sine theta here, which makes the equations nonlinear. And let's see what the nonlinearity does to the solution of the equation. And this is, of course, where MatGrapher becomes useful, is that you can solve these equations and plot the solutions very easily for things you can't easily write down. So let's change this to sine theta right here. And it looks pretty much the same. I get an oval. It's a little bit inaccurate because I haven't changed the time step yet. And if I keep going outward, you can see what happens. Eventually they don't look like ovals anymore. It's starting to look a little squarish. And if I keep going, I actually get the solution becomes kind of crazy over here. But that's okay. I can go back, change the time step. Always have to do that, and then refresh, recompute. Still spiraling outward. Let's change it a little bit more. A little bit better. Let's just leave it like that for the moment. And think about, we don't have to go out as far. Okay, now let's think about our initial conditions. So what we have here is, let's change this to alpha so we can get different initial conditions. Now remember here what x is. X here is the first equation and it corresponds to theta. So what I really should write over here is theta, just to remind myself, and this is omega. Okay. Okay, so now I'm getting different initial conditions. Different alphas correspond to different angles. So this is how far am I pulling the pendulum back before I let go. And since the initial condition for y is 0, I'm not giving it a push. Okay. But let me give it a push in the minus direction and see what happens. So remember, y here is the angular velocity. And so I'm starting it down here and it's spinning around in the other direction because omega here, remember, is the derivative of the angle. So it's an angular velocity. Okay, so there's our more accurate solution. Now, one of the things that's nice is if we make the range of the initial parameters, the initial angle and the initial angular velocity, that is the initial conditions, over wider ranges, we can search for new types of solutions. So let's do that. Let's vary the initial velocity, the initial omegas, over a range. Too many values, but it lets us do it anyway. Okay, can zoom in and see what our solutions look like. As always, we should always check to see if we have the right time step. Okay. Changed it a little bit. Okay. Now let's make the range of velocities a lot higher. So let's make it go in steps of 0.6, but instead of going up to 1.2, let's go all the way up to 3 and recompute everything. Now notice I'm getting these square solutions and a completely new type of solution. But let's make sure that it's real by varying the time step. Okay. And it's more accurate, but look at that solution still exists. Now, what does that mean? We're getting two different types of solutions out of this nonlinear coupled ODE system. This part right here is just the pendulum going around and around. And this one is going over the top. Here it just oscillates back and forth around theta equals 0. And in this case, it goes over the top and back to the bottom and over the top. And basically what that means is I've given it an angular velocity as an initial condition that's so big that the pendulum just keeps going around and around over the top. Goes around over the top. Here, it just oscillates back down here at the bottom. So I have found with my nonlinear equations a second type of solution. And MatGrapher has made that quite easy because it allowed me to vary these parameters over large ranges and see if I could find new types of solutions. That's pretty great. And of course, you can label and export just like usual. It raises the question, however, if I could possibly find even more solutions. And this is where the concept of a vector field comes in. What a vector field is you can imagine that what's happening is, like, I take this curve, there's a slope right here, and there's a slope right here, and there's a slope right here, and there's a slope right here. And the same thing everywhere else. There are these slopes. And so one of the things is if you knew what the slopes were everywhere, like up here and down here and over here, you can imagine getting a sense for what the total solution is. That is, what if I start right here? Where would I go? What if I start right here? Where would I go? And so plotting the derivatives, that is the right-hand side here, if I could plot the derivatives everywhere, I get a sense for what all of the solutions look like. And I don't need to vary over these guys. So let's do that. Let's go down here and do new equation. And what we're going to do is we're going to define a function. I'm just going to call it f here. And that's going to be the derivatives. Okay. So I'm just going to simply type in here what I have on the right-hand side. So y here minus w naught times sine x. That's my derivatives. And I'm just going to store that in this variable f. Okay. Now, since I have it stored, I might as well remove it and put f of x and y here. Okay. And it's always a nice thing to do that anyway. It's very convenient because then you can just change it in one place. Okay. Now remember, always go back, change the time step. Okay. There's our solution. Okay, more accurate. Now we're going to add an equation from template. Now choose vector field and choose the second one because we have a coupled system. Okay. Now on the right hand side, put the derivatives, f of x and y. And there is our vector field. And now you can see how if you follow these vectors, you can see all the possible solutions. So you see some that would yield circular solutions. That's the pendulum going back and forth. Notice here you can customize everything. You can, as usual with MatGrapher, you can change the line types and everything. But you also see in the vector field arrows that don't go around in circles, and those are the solutions where the pendulum is just spinning like a propeller. Okay, here I'm changing some of the line styles on the arrows because, as usual, everything in MatGrapher is completely customizable. And so you can go through this inspector window and change everything that you need to. Okay, but let's move on. Now, one of the things that you might have noticed, and this is an important thing about the way MatGrapher does differential equations, is that we solve the same equation, the harmonic oscillator equation, which is a second order ODE, as a second order ODE, and we also solved it by writing it as two coupled ODEs. And when MatGrapher plotted them, we got graphs that looked extremely different. Why is that? Now this has to do with the way you take your differential equation and write it in a form to put it into MatGrapher. And this illustrates why you have to keep track of that. And it can be very powerful. When we wrote it this way, we were imagining that y was a function of time and that these two dashes here meant the second derivative with respect to time. And we understood that we would call x t, so this was really time down here, not x, and the double slash notation here was the second derivative with respect to time, and we understood that. So when we got a solution, we got what we thought, y equals cosine omega t. Okay, in this case, omega is 1. And so we get this nice sinusoidal thing versus time. Now, we did the same thing over here. We wrote this equation as two coupled ODEs. Here's the derivative with respect to time. So we have a single time derivative, but we have two equations. We have the initial conditions and we have the derivatives. But look what it did when it plotted it. It actually plotted x here and it plotted y here. Okay. But what are these things? X, in this case, if you remember, was theta. So this is actually theta here. And what was y? Y, if you remember, was omega. Okay, so what happened to the time variable? There is a time variable here, for sure, but what's happening is time is stepping this way. So it's two ways of plotting the same thing. Here we see what essentially would be theta versus time. Here we're seeing theta and omega, and time is varying along the loop. Now this leads us to a really important concept in differential equations, and that's the concept of a phase space. And I'm going to use a new set of equations here called the Lotka-Volterra system to illustrate this. And this is a whole part of differential equations called nonlinear dynamics. And in the field of nonlinear dynamics, we often use this concept of phase space. And that is what Matt Grapher likes to do. So let's go through that. So these are two equations you can see in terms of R and W. You can see that they're nonlinear. There's like a growth term here, alpha R. There's a nonlinear loss term. It's R times W. That's why it's nonlinear. This W equation is also nonlinear. There's a growth term here. It's plus R times W. That's a nonlinearity. And then there's a loss term here. And these equations in nonlinear dynamics were very famous because they describe everything from the way your immune system competes with a disease that you got. In economics, it describes competition in marketplaces, complex chemical reaction dynamics and mixtures of chemicals. And the example that I'm going to use here is predator-prey competition. So in general, when you have things competing with each other. So in this case, the notation I'm using is R here is a rabbit. That's the prey right here. And W here are the wolves. So this is the rabbits breeding. When there's a lot of wolves, the rabbits start to get eaten. When there's a lot of food for the wolves, you get more wolves, and eventually the wolves will die off if you don't keep feeding them rabbits. So in nonlinear dynamics, we often want to plot in what's called phase space, is we don't want to know necessarily how R varies with T or how W varies with T. We want to know how R varies with W. And when we plot R versus W, as T is varying implicitly, that's called phase space. So let's see how that works. So here I've already typed everything in just to save you some time. So up here at the top, I have the different parameters so that I can vary those. And then after that, I have the derivatives, the right-hand side of the differential equations. Here's my coupled first order ODEs. Let me turn it on. Make sure that I'm getting a good solution, change the line width, change the line color, sort of customize it, make sure everything's okay. And what you can see is I get this shape that is called the phase space. And what it means is the x variable here, let me cross it out, is really the number of rabbits. And the y variable, there's the vector field on there, so you can see what the solution space looks like. Another thing in nonlinear dynamics is very common. You can see what happens here. I start off with a small number of wolves and a small number of rabbits. The rabbits will breed until they get to be a lot of rabbits. And then as the curve goes this way, I follow the vector field. You can see what's happening. The number of rabbits is going down. It's going to the left, but it's going up. That's where the vectors are pointing. And that means the number of wolves is increasing. And so that goes up. The wolves get to be greater. Pretty soon, there's not very many rabbits. And when there's not very many rabbits, the wolf population starts to go down until there's so few wolves that the rabbit population can grow again, and then you get this cyclic thing. And of course, from the vector field, you can see other possible solutions for other initial conditions. Now, sometimes you don't want to plot things in phase space. In nonlinear dynamics, it's very common to do that. But let me just talk about how you would go about doing this if you didn't want to do that. And Matt Grapher very much likes to take whatever you have and write it in terms of this x and this y. You probably understood that from watching this video. But sometimes you don't want to do that. And if that's the case, you might have to go beyond Matt Grapher. So let me just talk about just quickly, generically, how that usually works. In most other differential equation solvers, you write a vector of the variables you want to solve as coupled first order equations, and that equals some derivative on the right hand side. And what's nice is if I solve these, I can actually get the population versus time. So here I'm showing a population versus time. Instead of being in phase space, I'm plotting the rabbit population in blue. You can see it goes up. And then when there's a lot of rabbits, I start to get a lot of wolves, the predators in green. And I get a very different sense for the solution of the differential equation. And so Often you have to use something beyond MatGrapher. Here I'm going to talk about the Python solution, but it's pretty common to always write the equations this way, usually plot them versus time, and there's a generic way that these other solvers work, and this could be true for MATLAB, for R, Fortran, C, C++, whatever you program in. And in general, the way this works is you bring in the routines you need for your solvers. This just sets the parameters. This sets the derivative, which is d. This sets the initial conditions that you're going to use to integrate these equations. Then you simply integrate them and store the solution. And once you have the solution, you can plot the results however you wish. Here I'm plotting prey versus time and predators versus time, and I may want to look at it that way, but I could also plot predator versus prey, and I could get a phase space plot very easily. And so this is typically the way it works in other contexts. And one of the things that's nice is not only can I plot it in different ways that MatGrapher wouldn't let me plot it, I can also use different solvers and have different control. Like you notice I don't have too much control over the Runge-Kutta fourth order versus Euler, and I had to keep changing the time step. This one here is more adaptive. And so that's, if you ever go further in your studies or career with differential equations beyond what MatGrapher can do, this is generically how that might work in some other language. Okay, so just to finish, always remember that MatGrapher comes with a set of pretty excellent examples. And if you go into the examples in MatGrapher, you'll find one called differential equations. And I think now that you've watched this video all the way to the end, congratulations for making it this far, I think you should be able to understand everything that's in the MatGrapher example. So with that, I will see you back here at New Planet School, hopefully very soon.